brackets. Okay, hey, I'm going to go through a thin film problem with you. So we're going to pretend you've been playing with bubbles, because everybody should play with bubbles. We're going to say that the bubbles have an index of refraction of 1.4. And when you're looking at the bubble, you see green, which green light in a vacuum has a wavelength of 540 nanometers. And then the question is, hey, what could the thickness of the bubble be? Okay, so guess what? We need to start with a picture. So let's start with our picture. So I'm going to kind of sketch what's going on. So we have, okay, n equals 1.4, n equals 1, n equals 1. So I have a bubble here. Index of 1.4, inside is air, outside is air. Okay, I have light. There's my light. The light is going to come down and hit the surface. Now, some of the light is going to bounce off, because when it changes mediums, some of it reflects. So some of it is going to bounce off. Now, if you look going from an air to oil, bubble solution, that would be a hard reflection. So this is going to bounce back upside down with respect to that, out of phase. Okay, so far so good. So if you look, this is up, this is down. So far I'm out of phase with that. Okay, then part of it is going to keep going. Well, the part that keeps going is always in phase, so it's still orientated the same way. And then it's going to hit the surface. And again, part of it's going to keep going. I'm not going to draw that part. You don't want to know why? Because that part is not going to come to my eye. If I see something, so like if I'm over here looking down on this bubble, then I need to have light going to my eye. So I don't care about the light that keeps going this way. So part of it keeps going. Who cares about that? Okay. Part of it's going to reflect off. That's the part I care about, because that part is eventually going to go to my eye and I'm going to see it, and hooray. So this is going to bounce off like this. Okay. Now, this reflection here is going to be a soft reflection, okay, which means it's going to bounce back right side up, so it's going to stay like this, and it's, again, part of it's going to bounce off of here, right? I don't care about that, okay, but then part of it's going to keep going. I care about that because that's the part that's going to get to my eye. So this right here, guys, is really crucial that you draw this out, because that's going to tell you the starting condition. So the starting condition for this problem is out of phase. Okay? So again, is it always going to be out of phase? No. You have to draw it out. Okay? Go through this process. So this is, the starting condition. Okay? Which is also explains, guys, why if there is no path difference, like your bubble is getting really, really skinny, you actually don't see any color. The reason you don't see any color, if there's no path difference, your starting condition and your end condition is always going to be the same. If they're always the same, it's out of phase. When we're talking about light, out of phase means no light. Okay? But that's going to be your starting condition, is this. Then, okay, if I can see green light, and this problem says you can see green light, so the ending condition depends on the problem. If it says it cancels out blue light, then the ending condition would be out of phase. But in this case, it says you can see green light, which means the ending condition, okay, is going to be in phase for green light, because I can see it, okay, in phase. So if I am going from out of phase to in phase, that means my path difference has to be off by a half a wavelength. Okay, so if I want to set it up, I could set it up like this, where this would be, I'm off by, this could be 0, 1, 2, whatever. Okay, is everybody with me so far? So far so good. Yes, yes. Okay. Then now we have to think about, well, where is the path difference occurring? Okay, well, the path difference is occurring in here. In fact, if you look, here's the path difference, down and back up. okay? Which, if I label this distance t, really my path difference is going to be 2 times t, okay? Now it's maybe a teeny tiny bit bigger than 2 times t, but you can imagine it's going to kind of going straight down, straight up, okay? So my path difference is 2t because t, 2t, okay? 2t equals m plus this, okay? But here's where you guys got to be careful, okay? When I go into a different substance, okay, my speed changes. My frequency doesn't change because it stays green light. So if my speed changes, and you can think about this, if this goes down and this stays the same, that has to go down. And this is where, well, how do we figure out how much this goes down? Because that's going to be the same as this goes down. Well, this is where you think about the index of refraction. So n equals c over v. So if I do this, okay, remember what does index of refraction mean? It means that the light is traveling 1.4 times slower in that medium, which means my wavelength in that medium is going to be 1.4 times less. So if I wanted to, really it's going to be the wavelength divided by 1.4, okay, because again, that's where it's occurring. So if I wanted to actually solve this problem and say, hey, give me some values for t, I could say, well, the minimum value would be when this is 0. You know, I'd plug in 540 nanometers here, do some math, I would solve for t. Then the next minimum would be when this is 1. So I'd have 1.5 times 540 divided by 1.4 divided by 2, and I'd get my t. And then, in fact, any integer number here would allow you to solve it for your different thicknesses. So, but just to summarize, remember, guys, picture, 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 and then figure out your starting condition from your picture. Remember, ending condition comes from the problem. In this problem, we could see green light, so my ending condition is in phase. Bye, kids.